physics students. It's Mr. Dillick here, and I'm going to be walking you through the notes for Chapter 2 in the University Physics textbook. Remember that the purpose of these notes is to, for the most part, to help clarify the main points that you're seeing in the text. Of course, because this class is run more like a college course, I'm expecting that you're reading ahead and that you're trying all the little test your understanding questions and asking me questions that you may have during our class time. But here, what I want to do is just, go through and talk about the things that maybe you need a refresher on since your last physics class, highlight some of the most important things that are in the text, highlight some of the special applications or simulations that would be useful to you, and finally, to also give you kind of my take on the best way to go about doing things, proven strategies that I know have worked in the past. Although you can print this entire note packet, and you should, from my website, I've decided to break this long 36-page note packet into smaller sections. So I'm going to go over the first 6 slides today, which is really a physics concept review for Chapter 2. So let's dig in. One of the first things that I really want you to remember about physics from your first go-around in physics class is that physics is, more than anything else, a study of the natural world and the laws that guide the natural world. And because of that, we all may be looking at it a little bit different, so we need to make sure that we all agree on our frames of reference. By now, you recall that scientists have lots of disagreements about exactly how many dimensions might be out there. Some say just the 3 dimensions of space and the 1 dimension of time that we can all see and agree upon. Others say, according to string theory, that there may be somewhere between 11 and 20-some dimensions, curled up in small, tiny balls that are everywhere all around us, but we can't easily see them because of our perspective. That's all really interesting. But for classical physics, which is kind of where this advanced physics course starts, for classical physics, we're talking about the physics that we can really agree upon in the last 500 years or so. So what did Newton think there were? How many dimensions did Newton think there were? How many did Galileo think there were? Well, to this day, all classical physicists agree that there's the 3 dimensions of space, 1 dimension of time. Left, right, up, down, forward, and back. And so the best way to represent these are with number lines. And remember that number lines are useful because they contain both magnitude and direction. The magnitude being the number on the number line, and the direction being the 2 possible ways you can go on that line. So if you think about your old 3rd grade, 4th grade math class, when your teacher showed you your first number line, some of the numbers went off for infinity in one direction, and those were the positive numbers. Other numbers went off in the other direction endlessly, and those were the negative numbers. So just remember that number lines are a useful way for us to picture motion, because it gives us a frame of reference. It gives us a magnitude, how far, how long, how fast, that number, and it gives us a direction. Of course, you remember this from the physics the first time around. And then the cherry on top is that all physics quantities are measured with some standard unit. The standard units are ones that you should remember. The standard unit of position, which is going to include the derivative quantities, distance and displacement. The standard unit is the meter. The standard unit of speed and velocity is the meter per second. The standard unit of acceleration is meters per second, or meters per second squared. And then some of the tricky ones, mass, the standard unit is the kilogram, which often throws people off instead of the gram. And the standard unit of time is the second. The standard unit of work and force and power and energy and all those other things, we'll cross those bridges when we get to them. But just want you to remember that your answers for this course are not complete unless they contain a magnitude, a direction, and a standard unit. And we call these physics quantities because they can be measured with a number. So we'll be treating objects as particles, at least for now in this course. I recognize that, if we say Susie is sitting in her chair and she's spinning around and around, that the path that her hair takes as she spins and the path that her dress maybe takes and the path that her center of gravity takes are probably all slightly different paths. So to simplify that, we're just going to use the center of gravity as the particle that represents her entire body as she moves. That way we can simplify the physics for some complex motions. Remember that some physics quantities are scalar, some physics quantities are vectors. Scalars have a magnitude only, vectors have direction. Some physics quantities are averages, while others are instantaneous. Averages occur over a long period of time. Instantaneous quantities occur at a very specific moment in time. Physics quantities can be described in words, by equations, or by graphs. And you'll come to find that on the AP exam and on my tests, any one of these three is a sufficient and satisfying way to answer a physics question. If you're a verbal person and the best way for you to go about answering a physics question is just to give me a narrative, just describe it in your own words, that's fine. I'll accept that as long as all the physics that you describe verbally is accurate. However, a lot of times equations or using some sort of mathematics is a little better. It's a better way of doing it for us. And graphs are kind of the best of both worlds because they kind of illustrate something that you could put into words, but they have a nice mathematical background. If you can answer a question in all three of these ways, that's going to be the best, most well-rounded answer. If you can provide any two of these ways, that's good. And if you can only do one, well, that's good enough. But the more you could do, the better. Remember that although a lot of what we talk about is quantitative, some motions in physics are measured qualitatively. Rather than giving us a quantity, a number, a magnitude, a direction, and a unit where we're actually measuring it and putting a number on it, often what you'll see is that we describe these things in terms of quality. This thing's moving faster, slower, it's taking longer or a shorter amount of time. It's bigger, it's smaller. These qualities are often acceptable ways of describing physics ideas, but they're usually not preferred over quantitative ways. A quick basic review of some basic physics quantities. Don't forget, the most basic physics quantity that we talk about is position. If you have a number line and you're looking at a number line, that number line could be moving left and right, in which case we use X for the position. It could be moving up and down, in which case we use Y. It could be moving forward and back, in which case we use Z. Therefore, as we go on and talk about changes in position, you have to remember these axes and these number lines represent position, and the standard unit of position is the meter. So, although centimeters and millimeters and other derivatives of the meter work, meters, which you should convert it to in the end, and all of these things you should try and put in scientific notation anytime you can to ensure that you have the right number of sig figs whenever you're doing something quantitative with it. Don't forget that left and right, up and down, forward and back are both positive and negative directions. Generally, right, up, and forward are considered positive. Left, down, and backward are considered negative. Time is technically the fourth dimension here. So you can see 1, 2, 3, 4 dimensions that make up the basic understanding of the physical world around us. Time should be measured in seconds whenever possible. And time technically is a vector because it itself can be put on a number line, but we tend to treat it as a scalar quantity because the only time we have negative time is when we're looking backward to something that already happened. If we're looking forward, that's going to be positive time. Distance is a scalar quantity. We use d for distance. And distance is a total measure of how far something moves. That is, if something changes direction, we pay no attention to it with distance. If something moved 5 meters to the right and then moved 3 meters to the left, the total distance it moved is 8 meters, and we don't care about the direction. Displacement, on the other hand, is a change in position on one of those number lines, and it is a vector. That means that direction does matter, and instead of a total measure, it's a relative measure. That is, we really want to compare it to something else, some point of reference. A lot of times that point of reference is the origin of that object, but not always. When we start talking about the difference between speed and velocity, we recognize that both of these are rates. That is, now we're taking the most basic dimensions of our universe, space and time, and we're combining them together and describing how that position is changing with time. When we think about how this position is changing with time, there's basically two ways that that happens. One is speed, which we tend to use s for, and it is a scalar quantity. And really, the best way to think about speed is it is just the magnitude portion of velocity, because velocity is a vector. Because velocity is a vector, you really should never just put v by itself. It should always have some subscript that includes the direction, where no such thing is required of speed. Basic equations here are that speed, a scalar, is a relationship between distance, another scalar, and time, another scalar. So this equation includes essentially three scalar items: speed, distance, and time. Velocity is a little trickier than that because there's different flavors, but essentially, when we talk about velocity, we're talking about the relationship between displacement, a change in some position, and a time interval. So I just want to make a notation point here. When we look at this and we see that time here, I just put a t, and time here, I put a delta t. Basically what we're saying here is, well, because this is scalar, we don't really treat it as an interval. When we put the delta in front of it, what we're really referring to is something called a time interval. In other words, a long period of time. If you're going to include a direction on your velocity, you need to make sure that whatever position you're looking at matches it. And then there's acceleration. When looking at acceleration, we need to realize that acceleration itself is also a rate. That means you're comparing one of those variables, one of those quantities we just looked at, to time again. And when you're dealing with acceleration, we use the letter A for acceleration. Acceleration is considered a vector, which means it does have a direction, and therefore it should have some sort of subscript that goes with it. And acceleration is going to be a change in velocity over a time interval. So again, make sure that whatever frame of reference you're using for your acceleration matches the frame of reference for your velocity. The trickiest thing about acceleration is to remember that accelerations kind of go with forces. So that means something is going to accelerate anytime something is pushing or pulling on a particle. If that's happening in a constant way, we call it constant acceleration. And that means that the way in which the velocity changes is going to be really regular. So it's always going to double, or it's always going to increase by the same amount over time. This we like. This the math is easy for. Later on, we'll talk about how we have to use calculus to understand non-constant accelerations. Probably the only really important other thing I need to tell you about acceleration is that people get confused about whether or not objects are speeding up or slowing down. Remember that positives and negatives in physics mean direction. So a negative acceleration does not mean slowing down. It simply means that there's a force pushing or pulling in one of those negative directions, left, down, or backward. It is possible for an object to be have a negative acceleration and be speeding up if its velocity was also negative.